So tonight we're going to talk about everything you always wanted to know about the MCP, or afraid to ask, explained by Nina Rothwells. So ask me because I can help you. And here I am thoughtfully answering questions during an office hours during the online sessions this summer. So many of you took the online course with Chris, but did not get, took the online course with us, but did not get hands-on time with Chris and using the MCP. And over the last few months, I've gotten a lot of questions about MCP usage. And instead of answering everyone's questions individually, which I still will do, of course, I've compiled a bunch of the questions in this presentation. And then after the presentation, we will have a panel discussion with experts, MCP experts being us, and a nice demo with Chris. So what is the MCP meant to do? And I can see this is not the last draft of my presentation, so there's a couple typos, so I'm sorry about that. The MC tool that allows you to mix up and test numerous cleaning options. The concept is that each cleaning is customized to fit the needs of each artwork. And the MCP is a tool that helps you mix and track numerous cleaning solutions throughout the testing process. In order to perform the numerous cleaning tests, the MCP makes use of a solution set of stock solutions that can be combined in literally hundreds of combinations. And this gives you an idea of some of the solution sets that are in the database already. So the MCP workshop aqueous concentrate set is sort of your typical set, as is the MCP workshop and traditional and acrylic set has both components for traditional and oil paintings in it, traditional oil paintings and acrylic paintings. The caps is the cleaning acrylic painted surfaces set. And then there's some other sets, the carbopol gel sets and that heptane, xylene, isopropanol, acetone set. You can create your own set that could customize to working on whatever materials you work on, but these are sort of your standard sets. So what the MCP is meant to do. It's a set of solutions are combined to create aqueous cleaning options by varying such components as pH, chelators, surfactants, gelling agents, and co-solvents. And this is sort of your typical aqueous testing screen that we are going to talk about a little bit later. But as you can see, you've got these four components: the buffer, the chelator, surfactant, and gel mixed with water, and the option to add a co-solvent, make an emulsion. Down here, it tells you all of the components, the actual percentages of the different components, your pH buffer and your chelator conductivity here, and all of the different information about it. And then you could hit test it and continue on with taking notes about your cleaning test. So just like the aqueous, you can test solvents, and proportions of solvents or solvent gels are combined to create solvent or solvent gel cleaning systems. So here's an example of how you can sort of vary the content of the aromatic versus aliphatic versus dipolar versus hydrogen bonding components of solvents and create a diagram of where they fall within these and track your solvent testing results as well. And aqueous cleaning solutions can be combined with gelling agents, xanthan, or polymeric emulsion stabilizers such as Pemulin TR2 and solvents to make emulsions. And you would do that by going to your emulsion setup screen, hitting OK, going back into the cleaning test, and it'll help you add the right amount of xanthan or Pemulin and solvents to create emulsions. And solvent, surfactants, and aqueous components can be combined to create microemulsions. And here you have the different proportions of surfactant, water, and solvent here. And you would follow the dots. And if you have a blue dot, that shows that it will form a stable emulsion, and a pink dot shows an unstable system. So what can the MCP do for you? It's a reference to a wealth of information about chemical properties. and the relevant information for each component, including, but definitely not limited to pKa for weak acids, bases, and buffers, ion formation constants for chelators, critical micelle concentration for surfactants, Hansen solubility parameters for solvents, and azeotropes. And you should really understand that this information was all entered by Chris by hand, and he spent literally hundreds of hours looking at this information and entering into the MCP, and it's really a gift to the conservation community. So here is a page on the MCP for DTPA, which is a chelator, and you'll see how much information is on the chemical information page. So you have your molecular weight, pKa's, different buffer ranges, and probably most relevant for DTPA, formation constants for metal complexes, which is how you would decide whether to which chelator to use based on these formation constants for the different metal ions that you're trying to chelate. So what else can the MCP do for you? It is a source for providing information about health and safety, and a few, not all of the chemical property pages have the GHS health information on it, and green chemicals are identified in the database. But please remember that US law, and probably other countries' law as well, requires you to have your up-to-date safety data sheets from the suppliers of all your materials. So here's an example of information on acetone, and it has the GHS global harmonized system labels here. It has some actual information from the SDS, and Chris wanted me to point out that the SDS is dated from 1998. So you should probably have a more up-to-date SDS on file, but we agreed that probably not a lot has changed about acetone since 1998. So what else can the MCP do for you? Probably one of the most useful components is that it's a recipe and formula book for, like I say, 1 million different cleaning solutions, including aqueous solutions and gels, solvent solutions and gels, emulsions, and microemulsions. Recipes are just weights and volumes of materials. So although you should know about molarity, critical micelle concentration, HLB values, buffer type, et cetera, you don't need to know about them and calculate these things when you're mixing up your cleaning solutions. So here's an example of what I'm talking about in a recipe. It's just like a recipe, like making a cake. You begin with 83 mils of distilled water, add 1 gram of bistress distilled water, 1 gram of citric acid. It doesn't say create a 1 normal or molar solution. It actually tells you exactly what to do. The MCP is also a great virtual administrative assistant. It's a database of all the cleaning tests you've ever done, should you enter them into the MCP. You can record information about every cleaning test you do, including pictures of your dirty swabs, and you can print labels for all those little jars you have everywhere. Your copy of the MCP, I want you to know, is local to your computer. There's no link to the cloud or other MCP users, so you can put whatever you want in, and it's not going to be on anyone else's computer. I get that question a lot, and people are embarrassed to enter information, but no one else can see it. So here's an example of a testing page for a painting that I was working on last week. Here's a photo of the overall painting, and then a photo of the cleaning test. I used a pH 7.5 buffered citric acid solution with hydroxypropyl methylcellulose as a gelling agent. And I thought it had a great grime removal, and it was perhaps a bit slow, but I thought it did a great job. So that was what I used on that painting. It can also be a source to print out your labels. So here's an example of a recipe, and here's the label, and you could print out that label by clicking Q label for printing, and then you'd have a nice label for your bottle when you finished making that aqueous component. Oops. And sometimes the MCP can also remind you to use a clearance solution. So it will remind you to rinse after each test that you do. What the MCP does not do for you, it doesn't think on its own. It doesn't tell you what type of cleaning system to use. It doesn't suggest what to try next. And it doesn't tell you when to stop when something does not work. You still have to do all that on your own. But sometimes it does make suggestions. Like when you hit the no stop, when things aren't working for your cleaning, it might tell you to try to consolidate or do a mechanical cleaning or switch your pH. So it does have some helpful suggestions. So now that we've covered what the MCP does and does not do for you, I want to talk about what you should do and not do when using the MCP. There's not a lot of hard and fast rules for the MCP, but if there were, I would put them into this MCP do's and don'ts section. So do use deionized or distilled water to make solutions. Don't use tap water. Do measure the pH while making solutions, the aqueous solutions, and the conductivity when making the pH adjusted waters. And don't rely on uncalibrated pH or conductivity meters. So do measure the conductivity if you're so inclined. And I want to just point out here that there are applications in paper conservation where the conductivity is crucial. But for paintings, I like to tell people, don't get hung up on measuring the conductivity of the surface of a painting, because it varies widely all over the surface of the painting. And don't let the widely varying conductivity of the surface prevent you from cleaning a painting if other aspects of testing indicate that a cleaning is safe. Do know the difference between aqueous stock solutions for testing and aqueous cleaning solutions for use on artwork. When I get questions from people, it's often a confusion between these two concepts. So I want to take a little time to go over this. So don't use the stock solutions on artwork. Remember that they are 5 times more concentrated than solutions that one uses on the artwork. Do know that many of the aqueous recipes you find in the solutions database are for stock solutions, and I'm going to show you how to figure that out. The recipes for solvent gels are not concentrated and can be used on the artwork. And I also want to point that not all solvent gel recipes in the MCP form usable gels. However, any recipe that starts with the letter M should work well. And I'm going to show you right now how to find the recipes in the MCP. So here is a list of, from the solution set for the aqueous components. And if you were to look here, it'll say what it is. Like, for example, this is a pH 8.5 boric acid and sodium hydroxide at 10%, and it says pH buffer concentrate. So you want to look over here. If it says pH buffer concentrate, that means it's for the concentrated set of stock solutions, not to be used on artwork. Here's a recipe for a solvent gel, and it'll say type of solution, solvent gel. Now, if it has this little M in front of it, that's a solvent gel that works well. Any ones that don't have the M don't necessarily form stable gels. So just make sure that if you're making a gel that you use one of the ones that have the M. And here's another example of a label, just so that you could print out a nice label oh, sorry, this is not an example of label. Oops. This is my brain. So this is a formula for a stock solution. And I want to point out that it says pH buffer concentrate here. It says pH buffer concentrate here. And it says concentrate, do not use undiluted. So if any of the recipes have this in the on the page, on the MCP, don't use them on an artwork. And this is a typical formula for a cleaning solution. And they always say yes, clean recipe on them. They're green, and they don't say concentrate anywhere on here. And this is a typical formula for a solvent gel. So it shows you it has the solvent gel here, and then the nice label down here. So my question to all of you, and I can't see you because we're screen sharing, but can you use this on an artwork? And you could maybe put a thumbs up or a thumbs down or a yes or no into the chat, so we all know that you're paying attention. And the answer is no, it's a concentrate. You should not use it on an artwork. So more MCP do's and don'ts. So do use the components exactly as written. Don't make substitutions unless you know what you're doing. If you do make a substitution, make sure that the substituted chemical has the correct information in the MCP. Do know that the acids and bases in the MCP are chosen for their inherent properties. Acetic acid and ammonium hydroxide are used in the pH adjusted water because they both evaporate. Hydrochloric acid and sodium hydroxide are used in the aqueous components because they do not evaporate, allowing one to set the buffers in pH with at least relative ease because the acids and bases aren't evaporating as you're taking the pH readings. So this happens. I've even messed them up, I will admit. And this happens at most workshops, that somebody confuses sodium hydroxide and ammonium hydroxide. So do know the difference between sodium hydroxide, NaOH, and ammonium hydroxide, NH4OH. Don't substitute bases and acids, because remember, ammonium hydroxide and acetic acid will evaporate and the pH of your solutions will fluctuate due to that evaporation. So this is the big slide I want you to remember. If you remember one thing from this presentation, let it be this. Sodium hydroxide is not the same as ammonium hydroxide. So do know that the average MCP user without vast chemical knowledge should stick to the recipes as written. I'm sympathetic to international MCP users who may have difficulty obtaining all the ingredients and may make appropriate substitutions as long as they're appropriate. Do rinse cleaning solutions. Don't leave any cleaning solution on an artwork indefinitely. All aqueous solutions need to be cleared or rinsed. And as a rule of thumb, rinse with the pH adjusted water of the same pH as the cleaning solution. It's also a good idea to do a final wipe with mineral spirits, but only if the surface can handle it. Oil and water emulsions and microemulsions need to be rinsed with the pH adjusted water of the same pH as that emulsion. Solvent gels need to be cleared with a solvent that can dissolve the gel, which is usually a component of the solvent gel itself. And pH adjusted waters do not need to be rinsed, as the acid and base components evaporate. We're almost done. Do you understand that the software is all made by Chris and he does not charge for it? There will be some bugs, and there's some really simple tricks to navigate the bugs. Don't let the small glitches make you give up. Once you learn this trick, you could always navigate back home to the start page. So the trick is to tap on view, and then go to the layout mode. You see the little red arrow there. So you're going to click on that, which will take you to all these pages here. And if you go back to where it says start page, that'll always take you right back to the first page you get to, where it has the different databases and the choice to start and cleaning test. So in conclusion, the MCP is a wonderful tool that allows for the development of very precise cleanings of artworks. I hope that this presentation has inspired you to approach cleaning tasks with renewed vigor and curiosity. Really, the only way to learn how the MCP is to practice. And as always, do not hesitate to ask questions. I'm always happy to help out.
Thanks, Nina. That was so great.
Thank you so much.
Okay, so I think, do we want to maybe stop to see if there are any questions for Nina's presentation before we move on to Chris?
Yes.
Okay, so you should be able to unmute yourself now if you would like. And we did have, oh, go ahead, Charlotte.
Oh no, I was just gonna call one or two out from the general chat. Right, we had one from Madeline asking about if it's possible to make a custom set with citric acid and DTPA. Madeline, I don't know if you wanna ask a little more and if we wanna go live in the MCP or not, but you can make custom set, your own little set.
Yeah, citric acid and DTP are in the sort of most normal set already, but.
Oh, okay. Yeah, I'm a paper conservator, so I was just trying to narrow the scope of how many. I feel like that's the one area like I really need to dial in my testing a lot more like tightly and make it more, I'm in private, so I need to make it more time efficient. And so that's why I was hoping to try to create more of like a custom set that I can just jump immediately into that matches my existing solutions. So I tried to roll around with it a couple times and I just get to one point and then I'm totally stuck.
Okay.
Well, let's build a set.
Okay.
Let's see. Real quickly, let me screen share.
It's actually extremely easy to do, so definitely don't be intimidated by it. I think I have 10 different sets now.
Okay, so we're going to create a new cleaning set, and it's going to be aqueous, and it's going to be, can't remember how to spell your name. Close enough.
Paper.
We'll say paper, even though that honestly doesn't matter at all.
Sure.
So what pHs do we want to work at?
I usually go from like 6.5 to 8. That's usually the realm.
So we can do 6.5 bistrous hydrochloric acid. We get rid of that one. you want to do it in half-step intervals or full-step intervals?
Whatever is easiest. I know, I don't want
Full step, it'd be less. So 6.5, 7.5 bistris, 8.5 bicene. Whoops. 7.5 tris. There we go. So 6.5, 7.5, 8.5. Now we'll pick the appropriate pH
Chelators.
So we know we have to have them for 6.5, 7.5, 8.5. So we'll do 6.5 citric acid, 7.5 citric acid, and 8.5 citric acid. Not sure why there are two of them there. And we want to skip the EDTAs and we'll go straight to DTPA. So 6.5 DTPA. I have to re-scroll. Too far. 7.5 DTPA and 8.5 DTPA. Oh, sorry, my wife just pointed out I have an ammonium hydroxide instead of a sodium hydroxide. So we'll get rid of that one. And we want the 7.5 citrate with sodium hydroxide.
It's because Lark was paying attention to my talk.
Oops. And you can get the information if you click on there, but we want to move it over. Okay, so now we have our set of chelators to go with your set. We can now pick surfactants. We'll just say, since you're a paper conservator, you don't want to have any surfactants. Whoops. And there's a bug. We'll continue. Gel concentrates, not working. Ionic. Well, and now we see where I need to fix something.
That's where I ran into issue.
Okay.
Yeah.
Not you, it's me.
Oh, okay.
You may need to add one surfactant so that something populates, and you can just ignore it then when you do your cleaning tests.
Okay.
Or the next version, I'll fix this. I have my punch list now.
Okay, cool. All right, thank you.
So there was also a few questions related to downloading the software on different computer operating systems. And we've been talking about potentially, making some videos to help everybody with that. And I think we would plan to release them with Chris's new version of the MCP. So that's a work in progress. But there was a question about using MCP on an iPad. I haven't done that. Have any of you guys done it?
It's doable. The buttons don't work where you think they should. The iPad, I haven't done it in a while. Like 3 years ago, I loaded it onto an iPad and it pretty much worked. It was a bit slow and buttons are either too big or too small and some of the selections are really small and hard to see. It's a fairly complicated process. First, you would download FileMaker Go 18. Then you would take the FileMaker.fmpur file and use iTunes to transfer it into the FileMaker Go. And then once you've done that, it'll work to some extent. Like I say, I haven't tried it lately, so I don't know what of the new things it'll do and what it won't do. But if you're going to try it, send me an email and let me know how it goes.
And as far as downloading instructions, a lot of you have just a couple simple problems with downloads. And if you email me, I have been known to set up Zooms to help you do that. So if you're having download problems, especially on a Mac, shoot me an email.
And the common problem on Windows for downloading is you download the zip file and you have to extract the files from the zip file. If you run it while it's in the zip file, you get a number of errors and blank screens, but it'll sort of half run, so it's deceptive.
All right, well, if there aren't any other questions, maybe we'll move on to some demonstrations.
All right. So I'm going to switch cameras to, let's see. So you should see me kind of yellowish or orangish.
Yep, we can see you.
Okay, so probably best to put me on full screen if you have it in, if you have the Zoom in, whatever that's called view, the gallery view. You should put it on speaker view.
Should I turn it off?
Yeah.
Where do I do that?
On the corner. Sorry, we're just changing a lighting situation to get the glare off my forehead. Okay, so what we're going to do is go back and forth between the MCP. We'll have the MCP showing with the camera because I don't want to flip back and forth between screen share and not screen share. So we're going to start by looking at this piece of canvas. If you've ever taken the workshop, you've seen this before. Oh, that's not working very well. It's a piece of grounded fabric, probably from 18th or 19th century, that was done as a double canvas. So this was stretched on the stretcher bar with a ground to the back of the painting. Then the canvas was stretched over that's going to receive the paint, and then the painting was painted. So this actually works really well to provide atmospheric buffering and humidity buffering for the real painting. And this acquired 100, 200 years of natural dirt on it. So what we're going to do is find an area and do some cleaning tests. Feel free to interrupt at any point. We'll do the kind of standard with the MCP. Yeah, so Luke asked everyone, can you see Chris in this spot? So what we'll do is first, I've got my cups. Okay, let me go back. What we're going to do is I'm going to switch to the MCP. Bring the camera over here. So that's the MCP screen.
Oh, wow.
Okay, so can you get the screen? Okay, so there's the MCP. So we're going to start a cleaning test.
Whoa.
The artwork is a painting. Describe the painting, it's test canvas. What we're going to do is remove aged surface grime from aged oil paint film, unvarnished. So you can type anything you want into this little box. It doesn't matter, it just is for bookkeeping purposes. So we're going to start an aqueous cleaning test. And here we talk about using water alone. So let's first switch over to the canvas. And we'll do our test cleaning in this area here. And we're going to start with some distilled water, even though for reasons of hypertonic discussion, we usually don't use distilled water to clean an art surface. But we'll do a little test with distilled water. And we see not much is happening, which is not a surprise. So next we'll test with saliva or spit. Now this surface is a little odd. It's very greasy-like. So if we were to do one of those conductivity pH tests on it, we'd get practically nothing. We just get the reading of the distilled water because it's got that kind of fatty surface to it. It's not a varnish layer by any means, but there's a fatty quality to the surface that keeps the water from wetting it. So here's the test spot with spit, which is actually not bad. So the next thing we're going to do, well, come back to the screen. We're going to enter those couple of tests we did. So we tested distilled water first. We're going to test the rinse. Had no effect on the grime, no effect on the paint. We tested spit next. We had, let's say, a moderate effect and no effect on the oil paint, or the oil ground rather. So let's next try pH 5.5 adjusted water. And we're going to try all 5 adjusted waters and go through and just get a sense of what pH that surface likes best or gives the best results. So we'll start with 5.5. Let's go back here. And I've poured out my adjusted waters in the little cups across the top. So I have my distilled water, 5.5, 6.5, 7.5, 8.5. So we'll start with 5.5. We're getting a little bit up, but it's certainly not much. Well, maybe it's not even anything. And certainly ridiculously slow. So I'm going to go ahead and do the next one, the 6.5, and then we'll enter both those into the computer. 6.5. And you can see where it's dried, this 5.5 has made a little bit of a dent in the cleaning. 6.5. And to keep the spot small, I'm rolling rather than wiping and using a standard size bamboo skewer for the swab. You could certainly do, like a tiny swab on a toothpick and do much smaller areas with rolling instead of wiping. Okay, so not much there. Let's go back to the screen. So the 5.5 adjusted water, sort of very minor effect. I'll just say very minor. And we'll continue with testing. We'll try .5 test rinse. And that also had a minor effect, no effect. And it was about the same. Okay, so next we'll try 7.5. And we'll go back to the painting. And it's odd, kind of every time we do this, you get a little bit different results. So assuming the 6.5 has dried all the way, and I kind of rub for more or less the same time, the 5.5 is looking a little bit better than the 6.5. So our tests are saliva, 5.5, 6.5, and now 7.5, which is still wet. And remember, this is adjusted water, so we don't have to clear a rinse. This is our clearing a rinsing agent. And 8.5, pour some in the cup. So we're going to do the 8.5. Now we would expect that as we increase the pH, we're going from acidic, where we're holding that oxidized material down on the surface by the material being acidic and keeping the acid groups protonated, And as we go up to 8.5, we would expect just the opposite. We'll be deprotonating those acid groups, making them more soluble. So that's why we always start at the lowest pH for kind of traditional systems, traditional organic materials that age. So this one, I'm beginning to feel a little grippiness with 8.5. The swab is not moving quite so smoothly. So we're getting more of a interaction there. You can see as it's drying that we're getting a light spot. So let's go back to the computer and we'll enter those. So 7.5, minor effect, no effect on the ground oil layer, and about the same. And we'll do 8.5. And all these are about 1,000 microsiemens. It's still a very minor effect, although it is more pronounced. So it's the best of the pH adjusted waters. Okay, so now we're going to go and use the MCP, and it's kind of, we've established kind of what we want to know about the response of that surface to pH. And yes, we're using ammonium hydroxide and acetic acid in the adjusted water, so both components evaporate. So let's modify. We've got our sense of that surface as far as pH, and we know we can use our adjusted waters to clear whatever we're putting on and not dissolve the paint. So let's modify. And now we're at the MCP proper. We can start at pH 5.5. That actually looked pretty good. That and the 8.5 looked best on this little area we're testing. So let's modify the 5.5 water. Let's add a chelator. And for starters, let's try citric acid, citrate. So we're going to use 1 ml of the pH buffer, 1 ml of the chelator citric acid concentrate, and 1 to 3 ml of water. So we take our cup number 1 and a dropper, and we're going to take 1 ml of the 5.5 MES neutralized with sodium hydroxide concentrate. One ml of the citric acid sodium hydroxide concentrate solution, adjusted to 5.5. And 3 ml of distilled water. Since we're diluting, we do use distilled water. We don't use the adjusted water. We want to keep everything consistent. So we always use, for diluting the concentrates, we always use distilled water, just like we use distilled water to make the concentrates in the first place. So that's 3 ml of distilled water, deionized water. You give that a little swirl. Get a swab. And my swab fell off the stick. So now I'm going to skip over this area that's already been tested by somebody else, and we'll go to this spot. So this is working slowly, but you can see once it kind of breaks through, it's doing pretty well. So if you compare that with the spit saliva test, we're doing much, much better. So now is where the power of the, and you can see the swab is turned pretty gray. So what's the next thing? Before we think, before we talk, we clear. Remember, this has citric acid and sodium hydroxide. So it's essentially a probably a disodium citrate. And that will dry on the surface if we don't clear it and leave little crystals of disodium citrate. And we don't want that. So here I'm clearing with the adjusted water. And as often happens with chelators, you get a little bit of more cleaning action with the clearance. So I don't know if you can really see on the swab, but there's a little gray on the swab. So this is where the power of the MCP comes in. We now have a system that works. The question is that the best system for this painting? It's a little hard to tell what the artist's intent is on a piece of grounded fabric, but this is where we all bring our sensibility, our experience, our intuition to the fore and decide, is that the appropriate clean surface? So let's try a couple other things. Let's try, well, let's first, let me come back over here. Let's first enter this cleaning. So we're going to test it. It had a moderate to strong effect. No effect on the paint. It's still glossy. It still has that kind of greasy quality. Better than spit. And if we continue with testing, it'll remind us to enter a clearance solution. We remembered to clear the system, but here's that reminder Nina mentioned. And we cleared with 5.5 adjusted water. We clear with the same material pH that we used in the testing. So that test solution was 1.1% of MES sodium hydroxide, or 0.05 molar, 1% citric acid, 0.05 molar. The ionic strength was about 1.97 molar. The pH buffer brought 880 microsiemens, and the chelator brought 11,400 microsiemens. So the total solution is more or less 12,000 microsiemens. So we see as soon as we use a chelating agent, that conductivity goes way up. And that's the damning part of using a chelating agent, is your conductivity shoots really high. You know, ideally, we'd probably want to keep the conductivity around, oh, I don't know, maybe 3,000 to 8,000. So this is considerably above that. So we'll continue with testing. So this is where I'd normally ask, well, what do we want to do next? What can we change? We can change the pH. We can change the chelating agent, go from citrate to EDTA to DTPA. And we can add a surfactant. We could remove the chelator and try pH 5.5 with the surfactant alone. To go back to remove something, you go back to just buffer and we start again, we modify. This time, let's try a surfactant. So let's go up to 8.5, since that was the other one that seemed to work pretty well. And we'll assume we're getting a little bit more interaction, getting that grime off the surface at the higher pH, but we're not going to use a chelator, we're going to try a surfactant. Let's try EH6, EcoSurf EH6. So now we get our cup number 2. We take 1 ml of the 8.5 bicene buffer. We take 1 ml of the EcoSurf EH6 concentrate. And remember, these are all concentrated 5 times, so that in the end, when we dilute to a final volume of 5 ml in our little cup, everything's where it's supposed to be. And we take, again, 3 ml of water, distilled water. And so you can always check on your little cup that's got graduations on it that you're at 5 ml, which we are. Okay, so now we'll see what a lowish HLB surfactant does with a pH of 8.5. the surface feels a little bit more sticky right off the bat, even though we're using a surfactant, just by virtue of that, the higher pH. And we're getting a little bit of a different clean. We're getting a good amount of grime off. Actually, so what do we do next? We always clear. So what do we clear with this time? We're working at pH 8.5. So we clear with the 8.5 adjusted water. So now we have two test cleaning areas. We would look at that carefully. First, let it dry, look at it carefully, decide which is better, or if we're happy with either and we want to try something more. I'm going to hit it with a lot of light so you won't see anything, but I'm going to look to see how the gloss on those two spots compare. And I'd say they're very comparable. So in this little area, we could clean with either of those. There's a ever so slight difference. It shows a little bit more pronounced on the computer screen than it does in real life. So you could stand around with your colleagues and argue which is the more appropriate clean for that particular surface. Let's try one more. So that's solution number 2. And we have our cups with those different cleaning solutions. And we can go test other colors on the painting or whatever we're cleaning. We can come back and retest an area. We can test adjacent areas to make sure it doesn't overclean if you come back to the same spot. So test number 3. Well, let's enter test number 2 on the screen. Sorry. So we're going to test this. Same moderate effect, no effect on the paint. Same as 5.5 citrate. Surface remains. Let's see. And this time we cleared with 8.5 adjusted water. So let's do one more variation. Let's go back to chelators. And we'll decrease the pH back down to 5.5. Add a chelator. And we'll use the DTPA. Just see the difference between DTPA and EDTA. So again, we go back to using the 1 ml of the 5.5 citric. Oh, sorry, my mistake. 1 ml of the 5.5 MES. One ml of the pH 5.5 DTPA. And I don't know if you noticed, but I'm not drinking tonight. And it's not because I'm concerned about getting sloshed while working, but because I've got all these things on my table, and while they're very safe in general, they're not safe enough to be eating and drinking around. So we'll give my kitchen or dining room table a good scrub down before we eat here. 3 mils of water. And we'll see how that behaves.
Well, Chris, I have to say you just answered a question from earlier in the chat about whether you had your cocktail this evening. So
okay.
Thanks for that bit of advice.
That was before the saliva test. They were wondering if you were getting any extra oomph from the alcohol.
So here is the DTPA. And it's still wet, but to my eye, that looks cleaner. And that can be a good thing or a bad thing. And again, that comes down to our, aesthetic, what we bring to this painting, what our knowledge, what, in this case, it's not an artist, but what the artist's intent is, what the artist had in mind, how this interacts with other colors. Are we over cleaning? Are we under cleaning? So now we have kind of going back. We could always clean with saliva or spit and leave what is honestly a pretty heavy patina on that surface. And whether it would be even or not is another question. We could probably get away with even a lighter surface cleaning, just barely taking anything off with 8.5 adjusted water. And then here we have our three candidates. We have 5.5 citrate, we have 8.5 with the surfactant EH6, and 5.5 again with the DTPA. One of the things you'll notice is the DTPA has left that edge very clear and sharp. So we've got a very clear where the DTPA was and where it wasn't. It's definitely a little cleaner. I would say as far as cleaning goes, the 8.5 with the EcoSurf EH6 is a little bit grayer. The next is the 5.5 citrate. And the cleanest of those three are the 5.5 with DTPA. And we can continue this testing. We've tested 3 different solutions so far, plus the adjusted waters. And we've got a pretty good understanding of the surface. We could test other colors, look for residue in impasto, whether we're able to clear all that out. One of the nice things about the MCP, or using these kind of systems, whether it's the MCP or not, is that we have we can tailor for a much more direct attack in a sense, where it might seem scary fast at first. You can get in and get out quickly, so you don't have to work the surface for minutes and minutes and minutes. If you can get down, do the cleaning and stop before crashing into anything bad, you have the ability to clean something where there's, say, more grime and impasto in the lower areas than in the upper areas. You have less of a risk of over cleaning because you're putting something on that works quickly, clears the grime from the top and the bottom equally effectively. And you're not kind of taking something slower and rubbing and rubbing and rubbing and mechanically abrading the high spots to dissolve the stuff from the low spot. So there's something to be said for a system that works quickly, but kind of decisively, quickly, and then stops. It doesn't continue to work, it stops. And one of the ways you can test that is to go, we'll do it right now, we'll do an adjacent cleaning spot and make sure that where the cleaning tests overlap, we don't have over cleaning. So I'm going to do an adjacent spot to that 5.5 DTPA. I'm using the DTPA again. And you see it's working very nicely, but it's not, well, I guess it's too early to see if I'm over cleaning, but there's our adjacent spot. Again, clear with 5.5 adjusted water. Again, got a little bit more grime up with the adjusted water. And again, nice sharp edges, although not quite as sharp there. But do we see any over cleaning where those two overlapped? Not at all. So we know that this is doing its job and stopping. It's not like it's kind of chewing as it goes on. What would I use to clean this? I would be torn between the DTPA and 5.5, although honestly, I would try pH 6.5 and see, keeping things on the acidic side, but see how that all works with chelators and whether I'm happy with that. Maybe 6.5 with citrate will be as good or better. Maybe 6.5 with DTPA will be better yet if we want to go that far. But sorry, I lost my train of thought. Well, anyway, we can test multiple areas on our painting, figure all that out. I had something profound to say and it's completely escaped me. So let's do one more thing. Let's make a gel real quickly. It's been about an hour, so I'm guessing you're all getting bored. But we'll do set number 4 and we'll use xanthan because that's the easiest to mix up really quickly. we will use, oh, sorry, let me enter in, test it. We're going to say that was a, we'll say that was a strong effect. This is with the DTPA at pH 5.5. Still no effect on the paint layer. Strong. We cleared with the pH 5.5 adjusted water. And one of the changes I'm going to make on the next version is take off dangerous for what's good and say something like scary good instead of dangerous. So that's one of the big things to look forward to. So we'll continue with testing. So let's gel this. So we'll, yes, but modify, gel it, and we use xanthan gum. So now we're going to take a gram of xanthan gum, 7.5%. Use our little drug dealer scale.
So Chris, since you got a good cleaning effect with the surfactant and the chelator, why or why not would you try a test solution with the buffer, the surfactant, the chelator in this situation?
Why wouldn't I?
Why would you or wouldn't you?
I would be tempted to try all three together. Often, not always, surfactant with chelator doesn't do any better than chelator alone. And sometimes it actually does a little worse. So, but it's certainly something to look at. And sometimes it does better with the two together, with the chelator and the surfactant as kind of adjuvating towards each other, if that's a word. Okay, so we're going to do the same thing. We're going to do, we have 1 gram of xanthan. We'll do 1 ml of the 5.5 buffer. We'll do 1 ml of the 5.5 DTPA. And we will do 2 mils of water. Since 1 ml is the DTPA or the xanthan gum itself. Sorry, that's 1. That's 2. I'm going to give that a quick stir to just break up the lump. And I'm going to use my little milk frother. And here we have what is at the moment a slightly runny gel, but it will stiffen up over a few minutes. And we use a brush to apply the gel. Oops. And we'll just go right here. Apply it with the brush. Much less abrasion to the surface from the no cotton swab abrasion. It's taking a little longer because we're not getting that abrasive action from the swab. All right, it's starting to break through. One of the nice things about using the brush with the white nylon tip is you can see the color of the grime coming off, and if this weren't a white surface below, you can see it in contrast with the white bristles of the brush. So there we're getting kind of a nice slow action. So this would be great if we had impasto. We had to kind of work the lower areas of the impasto more than the upper areas. We could kind of work into that grime layer. Okay, so now we'll clear that. Again with the 5.5 adjusted water. And there we have the the test area. So let's do something, well, let's go ahead and enter this into our database. So we'll test it. It's the same effect as before, not surprisingly, same as ungelled. And we cleared again with the 5.5 adjusted water. So one last thing. Let's try making an emulsion. So we're going to add let's add some mineral spirits. So we'll add some Shell Sol 140 HT. Let's say 10%. So it's going to tell us to add 0.5 ml or 18 drops of our Shell Sol 140 into that little cup we just made. So let me get a dropper and my Shell Sol. Half a ml. So I'll give it a quick stir just to keep it from splashing around too much. And use the milk frother. And you notice, should probably do this with glove hand, but kind of cover it up so it doesn't splash out. So now we have creamy emulsion, not as emulsified as I would have thought. It's not as white and milky as I would have expected. But now we can take that with our brush. And my suspicion is it'll go through a little faster because it's got that mineral spirit, that solvent quality to it. And it's about the same. So much for my suspicion. I guess it's breaking through a little faster. There we go. So anyway, that's how you make an emulsion with the system. That's been added to version 10. So we'll clear that away. So I'm going to do another rinse. So here we have a system that is both water and solvent, excuse me. It didn't clean quite as nicely as the gelled system. But anyway, so that's where we are. And that's where we'll stop the demonstration. So let me switch cameras. And here I'm back. So any questions, comments?
Oh yeah, we've got a bunch in the chat.
Okay.
I'm not sure where to start though. What do you think, guys? Luke, Nina, what do you think?
Let's see. I was trying to keep track. So let me see. I think our first one was, if you're using ammonium hydroxide for the adjusted waters, are you making them fresh just before testing, or do you have buffered adjusted waters with sodium hydroxide in stock for testing?
Adjusted water only refers to waters made with ammonium hydroxide and acetic acid. The buffer solutions we use are in our mixed up sets. Those have sodium hydroxide. But remember, if you make a water system with sodium hydroxide and acetic acid, you will be left with sodium acetate on the surface, which isn't a good thing. So for adjusted water, we always use ammonium hydroxide and acetic acid. Once we have a system that we're rinsing with, you can use sodium hydroxide to your heart's content, but you realize you will have a residue left behind. Anything that has sodium hydroxide in it was guaranteed to leave a residue. Almost anything with hydrochloric acid in it is guaranteed to leave a residue. So for our purposes, we'll just say anything with hydrochloric acid as the counter ion will also leave a residue. So the only time you don't have to worry about residue is acetic acid and ammonium hydroxide.
I think the question was also about the concept that the pH adjusted waters won't stay at the same pH long term because they evaporate.
Oh,
So
okay.
as long as you keep your bottle closed and decant a little bit at a time, also they will mold if you don't put Germaban in them over long term. So you could mix up small amounts prior to use, or I just mix up a large amount, keep it closed and put the fungicide in it. And then once I use it up, mix it up again. So you don't have to mix it fresh for each testing session, as long as you keep them tightly closed and fresh. And keeping them in the fridge can also help with the mold, some people say. So,
but you want to use them at room temperature so let them warm up first.
Okay, and we had another question asking if distilled is the same as deionized water for these solutions when you're doing your dilutions for the concentrates.
For our purposes, they're identical, as is reverse osmosis water. There are different ways of making them, but for our purposes, they are super clean, no ionic material in them. So they're all the same for our purposes.
there's also quite a bit of discussion about what the pH of the distilled or deionized water is. And that's not as important because you're going to buffer it anyway or adjust it when you use it. So it's more important to have it be distilled or deionized than tap because you don't want any of the extra minerals or fluoride or anything like that in it.
Yeah, your pH will generally be slightly lower because a little bit of carbonic acid will be in there from the CO2 in the air, but that will be overridden almost immediately the moment you put something in there. So definitely don't get caught up on that if your pH is 6.5 or something for your distilled water.
It's basically meaningless to take the pH of distilled water. To actually do that is a really complicated process to get an accurate reading. When I was in undergraduate in chemistry, they were doing a lot of research on acid rain, and to measure the pH of acid rain and get a reasonably good number was incredibly difficult and precise. And people in different labs were trying to come up with different standard methods because it is so hard. And that has a little bit of stuff in it, but pure deionized water with only picking up carbon dioxide, that whatever you get on your pH meter, you may as well just make up a number. It's a number, but a pH meter can't read a non-buffered solution. So it's meaningless. So don't get hung up on that.
Yeah. So if you are still getting grime off during the rinse, would you rinse a second time? So that was, while you were clearing with your swab after you did your test. So if you're still getting grime off, would you continue, or would you perhaps go back to your cleaning solution and then rinse after that?
You can certainly go back to the cleaning solution if you feel you didn't get everything off. This is particularly true with chelating agents, and I suppose with surfactants as well, where if there's a lot of grime, the chelating agent will kind of get consumed. So you might want to go back with a fresh go with chelating agent solution. Rinsing twice is not a bad idea at all. You notice I did it once for most things and started doing it twice later. But double rinsing is a good thing, probably in general, but more so with chelators, because that's something we really don't want to leave behind. The other thing worth mentioning is, chelators can interact with the metal ions in paints and grounds. So from my point of view, if you could get the exact same cleaning with a surfactant versus a chelator, I would go with the surfactant, possibly at a higher pH. I've got no qualms with using chelators, but if you cannot use it, it's probably better than if you do use it.
So that actually kind of segues into some of the questions we were getting in the chat. Some of them were private to me about the dangers of chelators with pigments and the dangers of chelators with supports, and the discussion about whether it's better to use a chelator or surfactant. So I had said, and because we've talked about this in the past, that with oil paints, you're not as concerned if the paint is well bound because the pigments are usually encased in in the media, the ions for the chelators. But do we
And
see
remember,
otherwise?
Dissolving a pigment takes two things. First, that the chelator is there to take the metal ion away, but that metal ion has to go into solution. So we have to look at the solubility product of that salt that's the pigment. So arsenic sulfide, orpiment, realgar, cadmium sulfide, all those things, we have to look at how strongly that pigment is held together. So the example I was given in the lecture is you can soak vermilion or cinnabar forever in the strongest chelator there is, and nothing will happen because that mercuric sulfide is so insoluble in water. Basically, nothing will happen. So it's only a few pigments where you have to worry about the slight solubility of that ion going into the water where it would be picked up by the chelator. And as Nina said, in a well-bound oil film, those particles are really well coated with oil. So you have to not only get those ions out of the pigment, they have to get through a layer of oil to get to the water. So I think in practical terms, not much is going to happen. If you have a very underbound surface where you can imagine your pigments are getting wet with water, that's something they have to think about more.
Okay, so our next one is, how do we know when we've sufficiently cleared the cleaning solution?
Honestly, we never know. 2 rinses is better than 1. 3 rinses is probably better than 2. There's a point of diminishing return. Surfactants, there's probably a monolayer left behind after clearance. That's where if you clear with mineral spirits, you may kind of break that interaction between the surfactant and the surface below and let the surfactants float away, even though they're not soluble in the mineral spirits. Yeah, the question of what's being left behind is something that really needs further work. You know, I think we're not leaving much behind with proper clearance. These are water-soluble materials. We put water on at the right conductivity. We rinse them off. You know, our paper colleagues have been putting chemicals on paper and washing them off and are very comfortable that things like bleaching agents and that sort of thing wash away pretty well. Speaking for a profession I know very little about, so I may have completely wrong. But you know, I think tiny amounts left behind, probably not the end of the world. You know, so a few molecules of citric acid are left behind on the paint. It's dry, it's an inert salt. We know the surface of the paint is being bombarded with calcium and sodium ions from the environment. Those are never pristine surfaces. We've got grime hitting them. A few atoms of, you know, citric acid isn't gonna, I personally don't think is gonna be an issue. If you're uncomfortable with that, do what you can with adjusted water. You're leaving absolutely nothing behind. And I have cleaned objects with just, you know, if you can get away with cleaning something with adjusted water, that is the best possible solution for any conservation problem. You're not leaving anything behind. There's no downside to that. So, you know, if that works, then there's no residue issue at all.
Right, and just to clarify on that, when he's saying just cleaning with pH adjusted water, that's just pH adjusted water, not have, you don't put a chelator in that or anything like that, then you're right back to the same issue.
And that's what we started with on this test piece. You know, we looked at 5.5, 6.5, 7.5, 8.5 adjusted water. And if any of those had worked, would have been happy.
Okay, and so someone asked, why clear with the same pH? What happens if a different pH is used?
If we think in terms of really specific tailoring of our solutions, we clean at, say, 5.5, and we clear with 8.5, we may be kind of picking up stuff we didn't want to. I mean, that's why we liked cleaning at 5.5, was because we were really in control. By using a different pH, particularly a higher pH, we may push that cleaning further, which, you know, if we want to push it further, let's do it with the cleaning system, not the rinsing system. The other side of that is if you're cleaning with something like at pH 8.5, and we're pulling things up into that very slightly alkaline cleaning environment, and then we clear with a lower pH, we risk precipitating that material back onto the surface in the clearing process. So in fact, we're redepositing or have the potential to redeposit yucky stuff on that surface that's kind of been moved around and jostled. The worst example would be if you're cleaning with something like a resin soap that has to be at a higher pH, and you clear with a low pH, you'll actually precipitate that deoxycholic acid on the surface of the painting. And that's a really bad, bad, bad thing.
Okay, so someone asked if two solutions with a different pH work, almost the same, would you rather work with the one that has a similar pH for the surface of the painting?
I have my problems with measuring that surface of the painting, the pH of the surface of the painting. But honestly, I would say I'd rather work at the lower pH. Remember that we have that surface that's oxidized. That means there are all these acid groups poking up on the surface. The lower the pH, the more we're holding that acid group on the surface by keeping it the acid protonated, which makes it less soluble in water. So I would say use the lowest pH you can get away with.
Okay, and someone actually, there was a kind of a follow-up to that asking if you're getting almost the same effect, you're actually driving ions out of the surface of the painting. So I'm not quite sure what they meant. Maybe if you're using a very different pH from the painting's surface pH, are you driving ions out of the surface of the painting?
Typically, we think of ions moving in and out in terms of conductivity or ionic strength. So remember, we have the sponge analogy where you put a salty water on top of the sponge, the salt goes into the sponge. And we have some salt in our sponge already. We put distilled water, we pull that, the salts out of our sponge into the distilled water. So that's what we want to avoid. That's why it's not, ideally, if we could have chelating agents without those high conductivities, we'd all be happier. We wouldn't risk pumping some of those ions into the paint surface because we're hypertonic. We don't want to use distilled water to clear because then we're hypotonic and have the potential to wash ions out of our paint film, and that water will go in to where those ions were. So we're kind of swelling the paint film if we use too low a conductivity or too high a conductivity. So the idea with the rinsing is we want to pick a reasonable conductivity. And if we really knew what the conductivity of that surface was, if we could measure it with any kind of accuracy, we would probably want to keep our conductivity. Richard always said 10 times what the conductivity of that surface is. I'm not sure about 10, but certainly in that same ballpark. So the same or a little bit more or a little bit less, but we want to be in that same general area.
Okay, and then another one was what surfactants do people like to have in stock for testing these days?
The EH6 and EH9 are really great, and we know from the last lecture about EH6 and making the swollen micelle microemulsion, so that's good to have around anyway. I'm really liking the Pluronic F127, which I still haven't sent any of to poor Nina, but that's the one that's a non-ionic, that's a higher HLB than non-ionics are supposed to be, so it's a really strong surfactant. It's non-ionic. And as it is exposed to light, it degrades and eventually goes away. It breaks off ethanol and isopropanol groups with light exposure. And in the end, there's nothing left. So that's, to me, very appealing.
And then, of course, you always have your affinity surfactants on hand.
Correct. The deoxycholic acid.
Mm-hmm. One that I might throw in. Oh, go ahead, Nina.
I was just going to say that if people have surfactant questions, not to forget that there's probably 3 hours of content on surfactants on YouTube that we did.
I think with the European versions, there's maybe 5.5 hours worth of surfactants now. So yeah, definitely not there. I would also maybe throw in Surfonic JL80X. to have on hand. If I'm going to just use a solution just because I want that surfactant cleaning action, I'm not going to build a microemulsion or something. I'll usually go for the Surfonic JLADX first. Part of that is because it has to reach 10 times CMC, it takes 3 drops in 100 milliliters of solution. So it's physically very little surfactant, by volume in your solution. In fact, you have to make 30 milliliters just to get to use 1 drop of it to get to 10 times CMC, or you can dilute it otherwise.
And Marlipol for Europeans, we're not sure how that fits in there, but it's probably similar. I don't know about for making the microemulsions, but I believe it's a very small amount of the Marlipol. And it's easy to get from Kramer, where a lot of the Surfonic is not available.
Mm-hmm. Okay, so we have another question saying, I'm going back a number of sessions to ask this question, but you mentioned that the pH of wash water affects the compounds that will wash out of paper. Do you have a reference for that?
No, but I mean, this is kind of not answering your question in that, no, I don't have a reference, but it stands to reason if we have oxidized material, as you change the pH of the rinse water, you will protonate more or less of that oxidized material depending on the pK of that material. So as you increase the pH, go more and more alkaline, you will progressively wash out material that dissociates, becomes water soluble with progressively higher and higher pKs.
Mm-hmm. Also, just as a heads up, whenever someone is presenting and you ask them to cite a reference off of the top of your head, there's about a 5% chance that you'll get it. It's nearly impossible to remember when you're in the spotlight. Someone asked, oh, Kim, this may be for someone else, but so what about older photomechanical prints on clay-coated paper? Can this help lighten foxing? Kim, could you maybe elaborate on that a little bit? I definitely don't know anything about photomechanical prints on clay-coated paper, so if anyone else wants to jump in.
Clay-coated paper is really enough to know don't get it wet together if you get 2 pieces wet and they're next to each other. So my suspicion would be if you can find a pH and conductivity that minimizes the swelling of whatever is holding that clay coating on, you will have the least problem. And I would think that that's pretty much all you can do is to find, I don't know if the clay is held on by a gelatin system or some other system, but you would want to find the pH that minimizes the solubility of whatever that system is and the conductivity that minimizes the swelling of both the paper structure below and the clay, which will absorb onto the surface. Luke knows more about this, but the surface of clay is very active and it'll form hydration layers on that. So I'm assuming at some point there must be a pH or a conductivity where that is also minimized.
So we came to the end of the questions in the chat. So I'll throw out, there are 2 that people asked beforehand, and then there are some that are just kind of commonly asked questions. One of them is when you're testing an agarose gel and you're using an aqueous system, can you throw your aqueous system in the microwave with the agarose and heat it together and make your gel?
It depends. If it's adjusted water, no, because you'll boil off the acetic acid and ammonium hydroxide. If it doesn't have acetic acid or ammonium hydroxide, absolutely. You can take one of the MCP components, dilute it down to, you don't want to use the concentrate in the agarose. You want to dilute it to the working solution. And you can put that in the microwave with your agarose and make wonderful planchettes of material you can work with. Richard had done essentially that and was for a while was traveling around with a briefcase full of little discs of agarose with different combination of chelator. He didn't use surfactant, but different pH, different chelators, and all these gels, and he could just put them on a surface and see how it interacted.
Yeah, there is one thing you may want to watch out for. If you have a large amount of a metallic counter ion, you can get sparking and burning in your microwave. That happens sometimes. Or if you're using a beaker, that's a well-used beaker, there is sometimes little microscopic metal fragments in there, like ground into the glass, or Pyrex or silicone or whatever you're mixing in, and that can also cause sparking and burning in the microwave. So you do want to keep an eye on it while it's in there.
The last method or the best method so far that I've heard is when using the microwave, you do, I think is it something like 30 seconds the first exposure, and then 10-second intervals thereafter until it's at the melting point. Work in a plastic container rather than glass because it doesn't transfer heat as well. Be careful. The reason you want to do it in those 10-second intervals is because you don't want the aqueous material to get superheated and then bump and all of a sudden splotch out all this boiling hot material.
Whenever I use the microwave for heating things, I always go at half power
Well, that's an idea.
on everything.
Yeah. Good call.
The other thing is they've found that if you make the agarose gel, let it cool, and then remelt it, the quality is much better. So the people I know who have been using it always do that double melt before having it in its final form.
Mm-hmm. Another one that kind of comes up a lot is, people were noticing that you were using that white Taklon brush when you're using the xanthan gum emulsion. Do you ever use the white brush when you're just testing a purely aqueous liquid solution with no gel in it for a rough surface?
I have. Generally, I work vertically. So a free liquid on a brush will just typically make a drop and run down the surface. Although I have cleaned horizontally with a free liquid on a non-porous surface even, and working it with a brush. I cleaned a fabulous Klaus Oldenburg, one of the store pieces of potato, where the potatoes coming out and their chives on it. And just used a brush, and I used adjusted water with the sorry, my mind's shot. The one that breaks down, Pluronic. I added Pluronic to the adjusted water, used a brush on the surface, then blotted it out with a sponge, and then used just the adjusted water to do a rinse. And that worked really, really well. And it was all down to using a brush, no swab, could work into all the texture. So that worked really well. But on a vertical surface, it tends to run down.
Mm-hmm. Okay, everybody, we're coming up towards the end of the session. If you have any last minute questions, you can throw them in the chat or unmute yourself and ask.
I've got one freebie. If you use bamboo swab sticks, what I've done, I wrote about this years and years ago, but haven't mentioned it recently. You can take a magic marker and mark the tip to let it know what this is. And then when you have leftover Hextal or some other really strong epoxy, dunk the back of the swab into the Hextal, let it soak in, and then let it cure. So now you have a swab stick that's all absorby on the front end, on the pointy end, and on the back end, it's been essentially sealed in irreversible plastic. And you've got it color coded so you know that this one's been treated. And that keeps the things like acetone from running through the swab stick and getting on your hand.
Oh, Tiarna, would you maybe want to make that announcement again since everybody is here now?
Sure, I just put it in the chat. We're asking all of you to save the date of April 9th. We're going to have another guest speaker. This time it's going to be Mark Walton from New Access out in Chicago. And he's going to talk to us about computational imaging. But the focus of his talk is really going to be on, how we can all do this not necessarily having to use really high tech equipment. So, and an announcement will follow as usual, on our listserv. Chris will email you all, and hopefully we'll see you in about a month.
Yeah, so that'll be on April 9th, so a little over a month from now. In the meantime, we are going to, as always, upload this video so you can kind of follow along with the presentation if you're having issues. We're also going to do a couple standalone MCP basics videos, so going through a few basic functions in the software and showing you how to download it if you need some help with that. So we'll post all of those in our Facebook group, maybe on the AIC forum. As we move forward, we're going to try to make some of these videos a little more apparent on our Facebook group. Sometimes stuff gets buried in there. So if you have questions, you can look out there or send us emails and messages as usual. So thank you, Chris and Nina. That was really phenomenal. I always love watching you go through the cleaning process. And Nina, that was just a wonderful presentation. So thank you, everybody, for coming.
And remember, there's the EU European Remix Sunday for anyone who missed it and who obviously is not here to hear it. But if you know somebody who wants to, you can tell them about the remix. It's at noon, my time, 3 in the afternoon, East Coast time, and reasonable drinking hours for those in the EU.
Thank you all.
Thank you very much. Thank you.
Bye.
Bye.
Thank you so much.
Thank you.
I know that's a lot of information coming at you very fast. We have several questions. So we have maybe 5 or 6 queued up. So we can go ahead and get started on those. So we had one anonymous question, basically asking, there's all these components in the MCP, a few hundred, all these solvents and different materials. What is kind of a good starter kit? What are the essentials that are needed to start with the modular cleaning program? And that's something that we've actually talked about privately a lot. What is kind of your essential kit? So I'll throw that over to Chris.
I would say if you're talking about traditional paintings, probably the 4 pHs that we usually use are what you want to stick with. 5.5, 6.5, 7.5, 8.5. I would say you can probably do citrate as one chelator. You could probably get away with either EDTA or DTPA. If I had to pick, I'd put DTPA as the second chelator. 1 or 2 surfactants, maybe EcoSurf EH6 if you can get it from a supplier in your area. If you're doing traditional paintings with natural resin varnish, I would pick an affinity surfactant or resin soap like deoxycholic acid. And another surfactant I really like is the Pluronic F127, which is that weird non-ionic surfactant that's got a higher HLB than non-ionics are supposed to have. And it's the one that with exposure to light slowly breaks down and degrades into ethanol and then isopropanol, and ultimately there's nothing left behind. So that's very appealing, although I don't know what kind of time scale that happens on, but since we think hundreds of years into the future, eventually it will be gone.
Mm-hmm. And so for pH 5.5 in the MCP, it's what, MES and sodium hydroxide, Chris?
Yes.
And then we have
6.5 is bis-tris and hydrochloric acid. 7.5 is tris and hydrochloric acid, and 8.5 is MES and hydrochloric acid, and sodium hydroxide, sorry.
For 8.5, the bicene?
Bicene, you're right. I'm sorry, I got that wrong. So yes, bicene and sodium hydroxide.
Yeah, and then so that's 4 things right there. So you have your 4 buffers, and then maybe 2 chelators. So again, you've got, maybe citric acid and EDTA or DTPA, whatever floats your boat. And then maybe 2 different surfactants.
Maybe 3 surfactants.
3.
Yeah.
I mean, I love surfactants, so we can make that list as big as we want. But so EcoSurf
right.
pH6 is good. The pluronics are good. Marlipol is a good one for those of you in Europe. Surfonic JL80X is a good one.
And the deoxycholic acid resin soap for traditional varnish.
Right, and that's one of your, really necessary affinity surfactants if you're working with paintings.
And don't forget, we have a whole video about surfactants if you want to know more. So.
I think there's 6 hours of material on surfactants if you want it. Chris, would you actually be able to explain really quickly what an affinity surfactant like deoxycholic acid is and when you use it and why?
An affinity surfactant is simply a like dissolves like surfactant. So it's looking at the fatty end of the surfactant molecule and the surface. So the more the fatty end of the surfactant molecule is like the surface you're trying to pick up into an emulsion, into a micelle, the more interaction we'll get, and the more that structure of the surfactant will help pull that material in. So the thought experiment for a resin soap is if we have an oxidized layer of, say, Damar, and we take a bunch of Damar, crush it up, remove the damarolic acid, make a soap out of that acid, and put that on the surface, we will, like dissolves like, attract that, do our best to pull that Damar structure from the varnish into the water. So getting damarolic, whatever acid in quantity is very difficult, but the bile acid, deoxycholic acid, is a similar structure. And so we can use that structure like dissolves like to help pull the Damar or mastic up into the water solution. Another affinity surfactant that I don't use as much is abiatic acid, the acid from rosin.
Mm-hmm.
And then aluritic acid for shellac.
Yeah, and with the affinity surfactants, when he's talking about those shapes matching up, the way I've kind of started to teach it is to think of it as blocks of Legos. I don't know if you guys have those, but so Legos where they interlock, so you have one shape that interlocks with another shape, and then it just lifts it up off the surface. So you have one shape and then another shape interlocks with it perfectly, and then it just lifts it off the surface. So that's kind of the idea of the affinity and the similar molecular shapes that Chris is talking about.
I have a private question, if you allow me to. So it says, chelators and surfactants were and still are pretty much a don't among my colleagues due to concerns about residues and the fear that too many ingredients in a recipe may inadvertently interact with each other or with the object. Don't know if this is something that you could answer now here. What do you think about using chelators and surfactants and if it's too dangerous?
There are downsides to all these materials except for adjusted water. Well, even adjusted water has its downside. There are acetate ions which can interact with certain metals. We have to live with the realization that we are probably leaving small amounts of residue behind. And that's something that needs further study without question. The residue issue doesn't concern me much personally. I think in the case of a well-bound oil film where we've got our pigments coated with oil in the grinding process, I think we're pretty much talking about surface interactions of residue, and then also going down into cracks, which we can mitigate with things like cyclomethicone or gelling these materials, or even putting them into something like a rigid gel structure. So we can mechanically prevent stuff from going down through the cracks and into the canvas. But yeah, I mean, if you're concerned about residue, you're pretty much stuck with solvents, which are fine. They move things around. You can wash varnish down into the structure, but you're pretty much stuck with varnish, with solvent, and with adjusted waters if you want to avoid any kind of residue. And that's fine. If you want to be a little bit more selective and think about removing grime from a varnish layer before you take off the varnish layer and see if you can resolve that. I think that's a powerful tool. So you can use, say, a chelating agent to take the grime off a varnish layer, then evaluate whether that varnish layer is good enough to leave, possibly, you know, applying a little bit more varnish on top to resaturate it. But if it hasn't discolored sufficiently to justify its removal, we can then go step by step. We could then take a resin soap, affinity surfactant, and take off the oxidized surface of that varnish and leave the bulk of the unoxidized varnish behind. And then stop there and say, do we want to, is this sufficiently clean? Do we want to go further or not? And by using these tools, yes, there are downsides as far as residue questions go. I mean, the amount of residue is very, very small, but it is there. But the upside is that we can make these cleaning decisions and not be kind of stuck with whatever comes off in solvent is what we're left with, and what doesn't come off is what we're left with below. We can, with a resin soap, we can do something where a surface has been cleaned repeatedly with solvents. You solubilize the most soluble portion of the solvent and precipitate the least soluble, the most oxidized surface. So that will eventually form in the brush strokes as a blackish, dark brown material. And we can kind of get to the point with repeated cleaning, revarnish, that forms a visible enhancement of the brush stroke that wasn't intended by the artist. It's not meant to show the darkness in each low spot of that brush stroke. And by using something like a resin soap, we can remove that without damaging the paint around it. So we can, this is a very powerful tool where otherwise we'd have to come in with an incredibly strong solvent to remove that material that's so polar, that's so leached, that it remains in the crevices of the brush stroke. So it's a much gentler cleaning than coming back with something like DMF or DMSO or something like that.
Mm-hmm.
So it's all, it's what you kind of have to accept as the downside to these very customized cleanings. Yes, there is always a question of residue. So that's just life. And it's something I wish we could explore more. I mean, I hope we can explore more. Yeah, Han.
Oh, go ahead, Han.
I was wondering
Yes.
if this person needed to choose between, because this person was worried about the interaction between surfactants and chelators. If you needed to choose a solution with surfactants or with chelators, what would
Okay.
you?
Well, yeah, that's a very different question. Yeah. Go ahead, Chris.
I would probably personally say surfactant over chelator, just because we know the chelator is much more active on metal ions. And if we don't need to do that, I would go with just a surfactant. In practice, it's usually a chelator that does the job. That's because as the surface oxidizes and the grime oxidizes, we form those carboxylic acid groups that will then be bridged by something like a calcium ion or a magnesium ion. And we can wash that with all the surfactant we want, and we're not going to break that kind of bond between the calcium and the grime. The moment we put a chelator on, we pull that calcium ion out and the grime just floats away. So practically, you more commonly, at least in paintings conservation, you more commonly use a chelator than a surfactant. But if the two work equivalently, I would definitely go with the surfactant, which is why when I was doing that testing, pH 8.5 surfactant versus the pH 5.5 DTPA, there were slight differences in how that looked. But if I were happy with the 8.5 surfactant, I probably would have used that. The next thing I would have done is seen if 7.5 plus EcoSurf EH6 worked as well. And possibly if I could get that to work at a lower pH, I'd be even happier.
Mm-hmm.
Yeah, Han.
Okay, I have experience from paper conservation and ink corrosion treatment, and I have some, well, doubts about using DTPA because it's a really very strong chelator. And if you have a varnish layer which has turned more or less hydrophilic because of lead soaps, for instance, it could mean that these chelators are left after the treatment, and they could make
Uh-oh, I think we might have lost him.
destroy your. This is a real situation, but theoretically this would be possible. You don't remove them.
We lost the middle of what you said. So could you repeat
Sorry.
that?
Okay, the residues of chelators like DTPA, if the varnish layer has turned more hydrophilic because of lead soaps, for instance, could be a possibility, then its chelators could stay longer and they could enter the paint layer and destroy the paint, because the lake pigments can be, let's say the metal ions could be attracted to the chelator. What do you think of that?
Well, certainly with the lake pigments, if they're underbound, there's certainly an issue using a chelator with an underbound lake pigment. Lake pigments, because they're such small particles, dye attached to a metal ion on a substrate, they tend to wet really nicely with oil. So I think the lake is protected by a good layer of oil and a fat-rich paint. So like on a glaze, it's certainly not fair to say I've never seen a lake fade because I put a chelator on it, but I mean, that doesn't mean it hasn't been affected. But I think a fat, oil-rich lake is going to be protected from the action of the chelator by the hydrophobicity of the oil itself.
Okay, but if the oil has degraded because of the catalytic activity of the metal in the chelation, in the pigment, then there's a problem. As what happens with chromium, for instance.
This is why I'm glad I'm not a paintings conservator.
To me, I think the paint oil would have to. Yeah, I would think if the paint had degraded to the point of the oil being very degraded and very hydrophilic, I think there would be a lot of problems with that paint layer. I've never seen a paint surface that degraded, where I had the feeling that kind of that the intimacy between the oil and the pigment had broken down to that level.
Yeah.
You know, it's usually more of a surface degradation, and you can get a leathery surface with that kind of degradation, but I don't envision that kind of action going all the way down. Certainly, if you did have a paint that was that
I'm having problems with the connection today.
Oh, sorry. I was just going to say, if you had a paint that was that hydrophilic, if you put water on and it just totally soaked in, I would be concerned about using a chelator.
Yeah. Okay. I'd also say that if you have a paint that isn't, or a material that is at that point of deterioration, I would imagine there you would have some pigment transfer in your cleaning solution, whatever you're cleaning. So you would see that and immediately know, okay, something's going on. You would have, of course, stop at that point and say, okay, I'm not going to keep bleeding this pigment out at that point. So it's kind of like you're testing qualitative analysis and looking at what's going on is going to stop you from going past that point, you know?
Sure. Think before you act.
Or act while you're doing it, you know, either one works.
Yeah, that's true.
And look,
thank you.
So we have another question about how quickly you remove a gel. And I suppose the problem of leaving a gel drying on the surface and so on.
A gel on an intact surface, you know, is just easily removed, you know, first mechanically and then with a rinse. Same pH, if it's an aqueous gel, same pH adjusted water as the gel itself. Once you have a porous surface or a surface that has lots of cracks, that becomes more problematic. What I've been doing lately is to put down cyclomethicone D5 first as a hydrophobic layer, and that keeps the action of that gel very much on the surface. There's probably still a little mechanical pushing of that gel into cracks, but I think that's better rinsed off. You know, it's not forced all the way down into the structure, and a better chance of rinsing all that off. But again, that's the problem with a gelled system versus a free liquid system. Free liquid system will wash down and go much further, but it also washes back out. If a gel gets down into a surface, it's really difficult, if not impossible, to wash it out. So I would never use a gelled system on very, very matte paint. I've got a painting in the studio right now where you know, there's water damage to a very matte paint, and it's as you all probably know if you've ever dealt with this, it's really, really difficult to deal with without worrying about disrupting that matte paint or leaving residue in that matte paint.
Yeah, you know, one of the things when you're working with matte paint like that, one of the other techniques that you can use, again, starting with cyclomethicone to make that liquid hydrophobic barrier, and then instead of using a gel or a free solution, applying it to an absorptive textile like, you know, the Evalon CR or something along those lines. It's restricted by that, lay it on the surface, and then, you know, you can lightly, you know, roll a gloved finger or end of a pipette along the surface of that so it contacts it and absorbs some of that information. Working with very poorly bound 4,000-year-old matte paint on an Egyptian coffin, I use that technique for maybe, you know, 10 square meters worth of cleaning, and it worked perfectly fine, you know, with no issues of residue either, because then you can then come in with your absorptive textile after that while the cyclomethicone barrier is still intact and clear the surface with the clearing solution in the textile. So you avoid all of those issues right there if you're especially worried about materials getting down into cracks and crevices and things. There will of course be some, but it will greatly reduce it.
There's a very interesting question that says, why would you start with a mixture with a low pH instead of using a 7 or something neutral and then going down and up?
The way I like to think of it is in terms of an aged surface, where an aged surface is oxidized and we've got carboxylic acid groups on that surface. The lower the pH, the more we're holding those acid groups in the protonated form, which is less water soluble. So I always like to start at the lowest safe value. You're certainly welcome to start at a pH 7. I mean, that's a decision that's a perfectly valid decision. I just prefer the idea of kind of holding that surface down by using the lower pH. But that's one of the things where the MCP is not prescriptive. You can, you know, it starts at the lowest value and goes to the higher value. You can certainly start testing at pH 7.0. There's nothing, you'd have to make a solution of that. You could start at 7.5 or 6.5 if you like in the standard set. But actually there's a MFA set in there which has a 7.0 set of solutions. So you can start at 7 and work down or up. So that's entirely up to you, the conservator. But my personal preference is to start low and work up.
And then they say, if you will use the chelators at a lower pH than your best pH adjusted solution. So you find the perfect adjustment.
Generally, if I see didn't catch that. But generally speaking, if I see 6.5 works well, better than 5.5 as a adjusted water or buffer and say a surfactant, I'll often back off one pH step when I start a chelator, just because it's so strong that if I find 6.5 working best, when I add a chelator, I'll back off to 5.5 just to mitigate some of the strength of the chelator. And that's just from observation. There's no real theory behind that.
Yeah, one of the general trends with these chelators in the MCP is that as pH increases, again, you're deprotonating those the acid groups on there, and then you have more binding sites available. So, you know, citric acid, as the pH goes up, you now have 3 sites available to bind with an ion compared to 2 or 1. Same with EDTA, same with DTPA. So as it's going up to a point, it's reaching a higher, you know, binding affinity, more sites are available, things like that. one thing to be aware of with chelators like citric acid, EDTA, DTPA, above a certain pH, you can actually start to form insoluble complexes, especially with iron 3 and things like that. So above, pH 11 or so, I believe, specifically for EDTA, you have to look out for those kinds of things. So look at the pH range you're working with. Working in objects, we have a broader range of pH that we can work at. So you do have to be kind of aware of putting chelators into solutions at those elevated pHs, what can happen, what those interactions will be like.
And there's another question here. For surface cleaning on an oil painting, if pH 5.5 or 6 works pretty well in an oil painting and is safe, why would you use pH 8.5 when the oil painting could be compromised?
If 5.5 or 6.5 worked well, I would definitely use 5.5 or 6.5. I wouldn't go to 8. The sample cleaning I did, I just thought it would be interesting to see, because the 8.5 adjusted water did a much better job. At 8.5, we're not risking saponifying paint film. The pH isn't so high that we're going to make a soap out of that paint film, not like if we were at pH 10 or 11 or 12. It's just kind of the upper range of the safe range. But yeah, if I can work at a lower pH, I definitely would.
And then there are two questions here. First, would you start tests with gelling from the test number 1? So test something jelly, test something else jelly, and so on and so forth.
If appropriate for the surface, absolutely, you can do all your tests with gelled materials. Again, that's the nice thing with xanthan, is that it's simple to make those sample 5 mil gelled systems with the xanthan gum and the MCP. You can do it with pemulin, which is a better, has kind of a stronger surfactant effect, let's say. So it makes better emulsions, cleans better innately, but it's a little bit more complicated to work with. But either of those, 5 mils of xanthan or 10 mils of pemulin at selected pHs, you can do all your testing with that. You don't have to use any free aqueous system if you don't want to.
And then ascorbic acid is placed as a pH 6.5 buffer, while its pKa are 4.07 and 11.7. Why? Does ascorbic acid has other use than buffering?
Do you mean acetic acid? Ascorbic acid is vitamin C.
Those are pKa's, but yeah.
The only thing I've ever used ascorbic acid for is as a reducing agent for converting iron 3 to iron 2. And I didn't find it worked at any of the peaches I was working at. Oh, Han has a comment.
Citric acid also has reducing properties for iron 3 ions. Don't you think that's a problem, maybe, that they return into catalytically active iron 2?
Well, that's an interesting question, but Chris, you had the first comments. Go ahead.
Well, as far as Han's question, we often want to convert iron 3 to iron 2 so that we can chelate it out.
Make it soluble.
Right, exactly. So we'll often use something like sodium metabisulfite to reduce iron 3 to iron 2 so that we can chelate it out with EDTA or DTPA at a lower pH, so we don't form the iron hydroxide insoluble compounds. So that's the key to taking rust off a marble, is to use something like DTPA, calcium DTPA, so we don't strip the calcium ions out of the marble, but then have the ability to chelate the iron and also have a reducing agent in there to bring the iron 3 to iron 2, then chelate the iron 2 out of the rust stain.
This is one of the things that we talked about in the MCP group, I think last week, where mixtures of citric acid and EDTA, they're commonly used in industry for cleaning because of that exact reason. So the citric acid is reducing, And then you also have the EDTA chelating, but then also you have a very interesting complex between citric acid and ETA that forms an additional chelating complex that is very complex, and that can actually form a 7 dentate system, which is very nice for iron 3. So you can actually attack iron 3 and iron 2 at different levels in different ways simultaneously. So those mixtures work very nicely for that.
Thank you.
Oh,
We have the video on redox, reduction oxidation, where these concepts are further explained.
But yeah, certainly other, like Chris mentioned, certainly other reducing agents, work very nicely for that exact same thing. And we've used those very successfully at the Arizona State Museum with very stubborn iron 3 complexes, working with reducing agents and chelators like EDTA.
And a nice thing about the combination of citrate and DTPA is that it also buffers the entire pH scale. So from like 2.3 to 11.8 or something, it's a buffer no matter where you use it. So you then don't have to use an explicit buffer compound and you're controlling the pH.
Mm-hmm.
Okay, can I pose a question?
Sure.
Of course.
I know that Richard was never very fond of phytate. Why is that? Did nobody use phytate?
His problem with phytic acid, I'd never understood the argument, but it had to do with something to do with spin resonance. And he felt it generated a catalytic cycle through some kind of spin thing that I never quite understood, but he had a specific reason for that.
Does it have a particularly strong dipole moment or magnetic issue with spin states of electrons? Is that what he's talking about?
I honestly don't remember, but there was a...
I know. Okay, phytate stabilizes the iron 3 compound. Let's say the iron 3 phytate is the most stable. And it stays like that. And it's partly soluble, so it could be used for removing iron as well.
I think that's interesting. I might need to do some tests with that.
As long as you stay in 1-to-1 complexes, it's.
I can't say beyond what I just said about Richard's concern, but he did have a concern about it, and I just don't understand it.
It's a pity. I never had this discussion with him.
Okay.
We have a question about if you think phenoxyethanol is safe to use as a preservative, I understand, as conservant.
I think it's fine. As I recall, it forms a layer on the top. It's not water soluble. But yeah, anything that you can use at a very low concentration that keeps things from growing in your adjusted water and your xanthan gum concentrate, go for it. Benzyl alcohol has been used. The Germaben 2 is used with its issues. But if it works and you're using it at a very low concentration, by all means. One of the things I'm going to change in the MCP system is for the adjusted waters, I'm going to have everyone just make up the 6,000 adjusted water, 6,000 microsiemen adjusted water, and dilute it down for use. Those don't seem to grow yucky stuff as quickly, and 1 drop of a preservative in that will then be diluted to almost nothing when you dilute it down to 1,000 microsiemens. And it's just 1 less set of bottles to carry around. So that's my newest change, is that I haven't measured the dilution, but it's something like 1 to 10. So you would simply essentially use the 6,000 microsiemen adjusted water as a concentrate and dilute that down for use.
That links with a question that is further down about storing stock solutions. So is there a time limit for storing stock solutions?
Generally, adjusted water doesn't last long. With preservative, a couple months. I mean, it can last longer, but often you'll see something growing in it. For some reason, the Bridge S100 grows things very quickly. Most everything else is pretty stable. I've got some bottles that go back to 2012 that are still perfectly fine. but you just look and see if there's something disgusting floating in the side or mold growing on the bottle itself, to see if it's gone bad or not. But generally they last a long time. The set I used in that demonstration, I think were 3 years old, except for the adjusted water, which I made that evening before.
Carmen Aedo says that she uses boric acid instead of Vicin for pH 8.5 buffers. Is there any difference that you can tell?
It will work fine. I've always used the Vicin. One of the reasons we selected those buffers for the MCP is so that they would be compatible with enzymes, if you were to put an enzyme in the solution. I don't honestly know about boric acid systems, if they are compatible with enzymes or not, or all enzymes, but that's why we use the biological buffers. They're, buffer at low concentrations, and they are safe for enzymes and that sort of thing.
Yeah, I'll add one thing on that. The buffers that are used in the MCP are part of what are called goods buffers. He was a phenomenal scientist. But if you look up goods buffers, you can look at the particular properties of buffers like Vicin and why they're kind of special. They're actually very interesting and quite unique. So I wouldn't use regularly boric acid. You can use it, and I actually have in treating particular wooden artifacts, but Vicin is a very nice buffer. So if you can get that, I would stick with that.
We have another question about buffers, and it says, could we get away with just use 3, like trees, these trees, and boric acid, and maybe eventually TEA?
I would not use T-triethanolamine as a buffer regularly. Chris, you can answer the others. It's your baby, so go for it.
There's a lot of interest.
I would second Luke's comments to TEA. What happens is as the pH goes up, it becomes more and more alcoholic in functionality, and it's almost like adding a co-solvent. So you can get really, and that can be used for good, but you can do amazing things with triethanolamine, but using it as a buffer in and of itself, I think Luke's right. As far as MES, Tris, you can certainly use the borate buffer system. I know Richard was using it on a number of cleaning systems. I don't know the PK offhand. I can look it up real quickly.
9.1, something like that.
Okay, so you're not going to really be able to buffer something like at 7.5 with it. So, you just need to look at the PKs and see where a buffer is best for the pHs you want. So, you can pick any weak acid as a buffer for the MCP system, as long as you know its side effects. You can certainly use citrate as a buffer, but realize at the same time it's the chelating agent. So if that's okay, then that's great. You could use a mixture of citrate and DTPA as a buffer at any pH, realizing, of course, that they are chelating agents as well. So you'll be getting that secondary effect. But if you're looking for something with a chelating agent, you don't need to buffer that mixture at all.
And we have a question for you, Luke, because they've read your article on the wetting and they are marveled by it. But it says, there is a mixture of sodium bicarbonate, EDTA, citric acid, sulfonic, propylene carbonate, benzyl alcohol, and triethanolamine. What function has the triethanolamine on there?
Oh, okay. That's not where I thought that was going, but so in that, it was actually one of the things Chris was just talking about. It's an excellent co-solvent at the pH I was using it at, which was at about a pH of 11.5 for that particular situation. That was to remove a layer of soot that was deposited on a piece of porous pottery during a house fire. It was a very chemically complex material that was essentially insoluble. So I attacked it from multiple different angles, and that was the solution that finally did the trick. But the triethylamine did a couple things. So first was that extra alcohol solvency effect. Second is triethylamine can actually act as a co-surfactant. And so sulfonic GL80X was the surfactant used in that system. And I wanted very small micelles to attack the surface. So it was like the tiniest of micelles, but adding in that triethylamine makes that micelle a little more flexible. That's a little loose with the language, but it kind of makes it a little more flexible. And so it can actually solubilize a little more grimy, sooty material with that triethylamine. It kind of makes its way into the exterior micelle shell. So it can kind of stretch around things and reform and kind of mold around stuff. So that's what the triethylamine was doing, at least in my head. Who knows what it was actually doing on the object surface? That's what I thought it was doing.
Well, and that's analogous to adding a long chain alcohol to microemulsion system. It is, and so those alcoholic groups probably, and that, I think you're absolutely right, Luke.
Thank you. Cool.
I say, would you be able to suggest a starter pack for works of art made of paper?
I can't, Chris.
Paper objects or paper works of art on paper. Could you suggest a starter pack to clean it, I suppose?
Oh. I'm not a paper conservator, so I look forward to working with paper conservators to figure out an answer to that. But no, I can't. I mean, I think it'll have to do with things like having calcium EDTA and calcium DTPA, and the chemistry of citrate with calcium in paper baffles me because calcium citrate is not particularly soluble in water. So I don't know what happens when you put citrate and how that interacts with the calcium carbonate buffer in water or in the paper. But you know, citric acid can do amazing things. EDTA, DTPA can do amazing things. And if you protect the EDTA or DTPA with calcium ions to keep from stripping out that that alkaline reserve, I think there are amazing things that can be done, but it's outside of my area of specialization.
Yeah.
And sorry.
One step further would even be cleaning of photographs.
I'm not even going to approach that.
Yeah.
I am actually going to talk about that with Dana Hemingway. She was the senior photo conservator for the Library of Congress for about 15 years, and she came to the University of Arizona, where I'm at, a few years ago, and we've been meaning to get together to work on MCP solutions for photos, and then COVID hit. So as soon as we're both back in the lab at the same time, I think we're going to start putting some things together.
We have Justena asking, from your experience, when chelators, will chelators together with surfactants work better than those components separately?
My experience is that it varies. Generally, in my experience, the surfactant and chelator together, for some reason, don't work as well as surfactant as chelator alone. But that's just my experience. It's a surprise to me. You would think that they would work better together, and sometimes they do, but for a reason I can't understand or comprehend, often they seem to actually hinder each other.
Yeah, it really depends. And one of the things to remember is that, you know, not all grime and soil are equal. So, you know, like Chris is saying, it's highly situational. You know, you have very different soiling layers from object to object, painting to painting. So you just have to test. And that's one of the beauties of this system, is that you can test systematically and see what works best.
Yeah, I would second that. I mean, that's the whole point of the MCP, is that you don't go with what works first, you go with what works best and you experiment and see if the combination works better or not better. And you can make these solutions in a matter of minutes. So testing 12 combinations of pH, chelator, surfactant, gelling agent, adds maybe 20 minutes, a half hour to your testing protocol. So it just makes sense to kind of test all those variations.
Yeah, to echo that point, a month or two ago, we were working on a really complex brass bell that we were cleaning. And between 12 p.m. and 5 p.m., within 5 hours, I was able to test 35 different solutions on the bell and find what worked best. So I mean, you can go, once you get comfortable with it, you can just fly through these tests and go really fast and to see what works.
Private question, and it says, are there sustainable ecological solvents, for example, to dissolve organic substances such as cellulose nanocrystals? Do you have recommendation for sustainable ecological solvents for the removal of organic substances?
I think the best way to deal with sustainability is to go to emulsions. Microemulsions or conventional emulsions. We reduce the amount of solvent by putting it into emulsion in a water-based system if that's appropriate. So I think that's how we get to be more sustainable, is to simply use less solvent in these systems. The only thing to remember is an emulsion is not a friend to waste collection. So you never want to have water in your solvent waste. So an emulsion has to be stored separately from your solvent waste, because otherwise the water in there will can promote rusting in any kind of container that the solvent waste is put in. And also if it's used for feed into an incinerator for co-generating energy, the water could interfere with that and damage things. So you always have to keep your emulsion waste separate from all your other wastes. But I think you can be greener using emulsions in general.
Yeah, and there are lists from companies like Dow and a few other ones where there are these new greener solvents coming out that are replacements for other solvents. I would say similar to like global warming and greenhouse gases, we're not really contributing to a lot of that ecological waste as conservators, so that's not something I would really get too bent out of shape with the amounts of solvents that we're using. Besides the fact that green solvents is really kind of a crock. There's no such thing. So once you start to look into it and see what those solvents are derived from and the processes that go into making them, there's no such thing as a green solvent. So I would use what's safest for you health-wise and what's safest for the artwork, and just go from there, and don't maybe not worry so much otherwise.
Could you recommend an article on EDTA citric acid chelating method?
Oh yeah, I did put one in the modular cleaning program Facebook group, so I can maybe hop in there real quick and find it and then put it in here. But yes, there's papers.
Could maybe ask on a made surface, cyclomethicone D5 and then an agarose gel water solution can be effective and safe. I often dream of a rigid gel solvent system. Is there any way to make something similar? A rigid gel?
Well, agarose is a rigid gel. And if you want something more, that doesn't transfer agarose to the surface, it may hold the aqueous phase more or less strongly, but it is a rigid gel. There are the PEGI gels from CSGI in Florence. And again, you use those by just diffusing your aqueous phase into the gel itself, blotting and placing that on the surface. I guess I'd be hesitant to work with cyclomethicone with those, because I don't think you'll have the mechanical energy to push the cyclomethicone out of the way to get contact between the surface and your gel system. The cyclomethicone tends to form, kind of a monolayer on everything. And if you don't mechanically push it out of the way, I would think you would get very little interaction from a rigid gel into your surface with a cyclomethicone barrier.
Yeah, and then you have to get into, weighting it down, and that kind of defeats the purpose because now you're kind of squishing the liquid out and it's going to express onto the surface.
Right, right.
And they say, do you know a safe way to initiate a cleaning on an encaustic painting with dirt and grains?
Encaustic, obviously you'd want to work in an aqueous system. My guess would be something like, if you can't get everything you want off with an aqueous system, a chelator or surfactant, emulsify a little something like mineral spirits into there. So you get a little bit of action, but it's really a very small amount of mineral spirits. And I've never done this, but that would be my thought, as to kind of get stuff off that surface a little more strongly than you can do with just surfactant or chelator alone.
And there's a comment, can trees not be used to buffer to 8.5 instead of Bicin? This person, Luis, is wondering if Bicin has any advantages over trees.
If Bicin has advantages over Triz?
Yeah, because he says, can I use trees instead of Bicin, or why do you use Bicin? What are the advantages of Bicin?
I'd have to check the PKs, which I can do, but typically the closer you are to the PK, the more efficient a buffer is. So I would have to say, look at the PKs of Tris and Bicin.
So Triz is 8.07.
Tris is 8.0?
Mm-hmm.
So you could use it for 8.5.
Mm-hmm.
So
yeah, a little lopsided, but yeah.
So.
And Valeria Orlandini is asking, are you exploring nanoparticles with the MCP methods?
Not yet, but it's coming. If you were with us for the last session about, nanoparticles or nano structured fluids?
It says nanoparticles, so I let Valeria specify that.
For the nanostructured fluids, yes, it's the next version will feature those more directly.
I'm working with nanoparticles in relation to modifying coatings and things like that, but zinc oxides and those types of things. But other than that, I'm not really playing around with nanoparticles too much. Oh, so she did mean nanostructured fluids.
Okay, yes, well, definitely. I mean, I think that's the wave of the future. And the work by Baglioni and his group has been astounding. And I think to kind of democratize that a little bit and have it, go outside of their lab into a broader community, I think absolutely. And I'm looking forward to sitting down and spending a few days reworking the MCP to allow formation of those microemulsions where the continuous phase is water, and then we have the swollen micelles systems in that water at low concentrations and doing amazing amounts of work. So definitely. And de-wetting, the whole de-wetting issue.
We have Justena working on an oil painting, maybe 19th or 20th century, but she says the paint film is young and sensitive, and she's trying so far a pH 8.5 with Bicin, EDTA, Marlipol, and benzyl alcohol. But could you share any ideas on removing or retouching from this young and sensitive painting, oil painting?
Oh, Again, I would probably look at an emulsion system, reduce the pH, go down in pH to 5.5, so you're holding that younger paint down, and then emulsify into that. Start with something like benzyl alcohol and xanthan at 5.5, or at 6.5 you can use pemulin, which will be better, but it's at a higher pH. And start looking at emulsions to break into that. Also, some of the nanostructured fluids may work on a system like that. If the young paint, if the original paint is able to take water, you may be able to de-wet the retouch from the original that way. I had that work very well with the modern contemporary paint with some kind of overpaint, and use some of the Baglioni gels, Baglioni microemulsions, and just de-wetted the overpaint and pushed it off the surface. So it was very successful with that.
Another question about which materials do have, let's say, sorry, I'll start again. Which materials have potential to be removed with the wetting?
At this point, I'd say almost everything. Yeah, maybe Luke can answer that better, but
I would say anything.
I think the issue is, I'm sorry.
Oh, you go ahead.
Oh, I was just going to say, I think the issue is more the interaction with the substrate. I think you can take almost anything off with a de-wetting. It's just whether the substrate can take that as well.
Yeah.
So for example, with an aqueous, there are many things you can't put an aqueous system on, where you would want to use an aqueous system to de-wet. That would be, yes, my answer.
Yeah, and so that's one of the things where we need to come up with a few better water and oil microemulsion systems for those types of situations. As far as materials that could be de-wetted, pretty much anything that you're familiar with as a coating can be de-wetted just fine. Something like an epoxy, of course, that is very strongly covalently bonded to a surface is going to, that's not going to be possible. But anything that we normally work with as coatings can be de-wetted. But like Chris said, you have to really be careful, because if perhaps your paint is underbound, when you de-wet that coating, the paint is going to come with it. And if it's water sensitive, of course water is interacting with that surface, so you do have to be careful and keep your eye on those things. That said, that is also why we're testing new surfactants that enable you to de-wet much faster, so within a few minutes. So for a water sensitive surface, that could be very beneficial.
And they ask if you can use the de-wetting for surface cleaning instead of film removal.
No, de-wetting is only for film removal. You can use nanostructured fluids certainly very well for cleaning. So they can do different things depending on how you design them and how you apply them. Generally, when you're de-wetting coatings, you're going to tend to work with what are called swollen micellar solutions. And those have a larger solvent content, somewhere around 17 to 20%. For cleanings, I generally stick to microemulsions, which tend to have very, very low solvent contents for oil and water systems. So those have, solvent contents of, 1 to 3% or something like that, depending on the type of solvent. So yeah, those can be used to clean really well. Yeah.
Well, there's another question about hypertonic and hypotonic formulations. Carmen asks, before starting a cleaning test, do you measure pH and conductivity of the artwork? And I think it was a bit explained before that if you are working on a contemporary painting, you might, or you wish to measure conductivity, but if it's an oil painting, maybe it's not that essential. Or, well, I'll let you answer. Do you measure pH and
I find the measurement. I find the measurement process so error prone. that I've given up personally. If you can get better answers than I was able to get, I found the answers I was getting, sometimes I believed them, sometimes I didn't. So my feeling was, if I can't trust the answer, I may as well make up a number. So my feeling is for adjusted waters, for traditional paint, 1,000's probably close to, maybe 3,000, maybe 700 is isotonic. For acrylics, we know 6,000 to 12,000 microsiemens is generally isotonic. And to me, that's enough. And the biggest problem with the whole argument is that when you bring a chelator in, the conductivity goes so high. To try to keep a solution at a lower conductivity with a chelator is a losing battle. You'll either have a higher conductivity or no functioning chelator present. And that's just an unfortunate, reality of nature. We can't really do anything about that. So I don't find measuring pH and conductivity of paintings a useful tool. I just like to think in terms of that low pH holding that oxidized surface down, and trying to keep the conductivity in the 1,000 to 3,000 range, except when I'm using except when I'm using chelating agent, which is, it's going to knock the conductivity way high anyway.
I agree with everything Chris said, and I think that the issue is the thought that there is a conductivity or pH for a surface. And I think that, you're trying to look at it through a lens of this is a uniform surface, when in reality, it's so varied. You're getting different answers because there's different answers every square inch of that material. I've worked with objects where the range has been like 10,000 microsiemens difference from, one side to the other, because that's just what it is. One side had its back to the wall and one side had its, face to the front, and materials are landing on it. So you have different pH and you have different ionic content. So you have different conductivity. So it's really just kind of a guess. I tend to work around 3,000 and it seems to be fine.
And then the caveat is for paper conservation, particularly modern papers, conductivity is really important. So that's, that's one of the really interesting aspects of paper conservation now is looking at the conductivity of the surface. Not so much the pH, I don't think, but conductivity is really crucial.
Mm-hmm.
I don't know if you guys have any private questions. I don't have any more questions for the moment.
See, I think there was one someone asked me, and I may have looked over it. Okay, it was actually about pH and conductivity. So asking if you should use agar pellets for Hariba devices when measuring pH and conductivity of a surface. So Chris, what would you, if you were bound to measure it, what would you use, the agarose plug method?
I would use the agarose, not agar, but agarose. It's the more purified, and always make sure to test the conductivity and pH of the agarose itself, because there have been batches that have a lot of salt in them and have very high conductivity out of the package.
I actually had a really acidic xanthan gum once, and it freaked us out in the lab because we made our solution carefully, pH adjusted it, poured the xanthan gum in, and the pH dropped like 3 points. So
really, wow.
Yeah, it was at ASM, and I was standing there going, yeah, xanthan gum's great because it doesn't adjust the pH. Watch, and I put the pH dye indicator in, and it was 3 levels below where it should have been.
Wow, I'm gonna have to start checking my xanthans then.
I think with a gel, before the rule of thumb for gels, emulsions, whatever systems you're using, before it goes on the surface, right before whatever you're about to put on there, check the pH. Don't rely on what the pH was before you did that last step. Just check it before, and then you'll know.
Great. Any more urgent questions you have before these guys continue with their lives? It's your chance. Okay, can you give me examples of nanostructure fluids?
Sure. Yeah. So those are microemulsions, swollen micellar solutions, mini emulsions, oil and water in oil microemulsions. So that's actually a 3 layers encapsulated inside of micelle. There's tons of nanostructured fluids. Nanostructured fluids as a class, though, can just generally be thought of as anything with a surfactant in it. At that point, there's some type of nanostructure to it, especially for non-ionic surfactants. That's especially true. The structured part of that is just the fact that surfactants self-assemble and go to interfaces inherently when they're in solutions. That's the structured part. They do what they do when you put them in the solution, regardless of what you're doing to the system. So that surfactant will go to the interface between the liquid and the air and the solid in the liquid. So that's the structured part. So that's really all a nanostructured fluid is. It's kind of a ridiculously complicated name for some liquid with surfactant in it. That's all it is.
When Dr. Baglioni, when asked about it, he said, oh, we put nano in the title because you get more grant money if there are nanos in the grant proposal.
There it is.
So it says, do you have to subtract the conductivity of the agarose plug before measuring from the conductivity of the plug after measuring? Oh my gosh, this is too complicated for me. Do you mind reading it? Because my English is not that great. It's almost the last question. Yeah, it's the last question.
Okay. You want to just make sure that the agarose plug doesn't have much conductivity in it. I don't know if it'd be valid to say if the agarose plug had a conductivity of 1,000 and you measured the painting at 2,000 to say that the painting was at 1,000. So I think you just, if the agarose pellet beforehand, after soaking it in DI or distilled water, if it has a conductivity, I'd reuse the agarose for something else and get a new agarose that doesn't have much conductivity. And you don't have to check every time, just once per batch, if the batch is clear. And you always soak the agarose pellet in distilled or deionized water for some amount of time before using it to test the surface, just to wash out any ions. So.
Thank you, sorry about that. It was too complicated for me now. Maybe it's because it's 11:15.
Yeah, it's late. Don't blame yourself.
Great. I don't have more questions for the moment. Everybody's saying thank you already.
Cool. Well, thank you for the questions. Those were some great questions.
Yeah, really good.
I'll be passing all the video for the European Remix questions and answers, because I know people are finding it very interesting as well. So I know people want to see the American version and the European one. Don't worry, I'll pass it around.
Yeah, we'll post it in the modular cleaning program group. I don't know what it is, but you guys are just like dunking on the American audience with the questions. These were really great questions. So I may combine these into one thing, because this was a really good session and really interesting information. So thank you all for your questions. That was great.
Yeah, we have great participants. I'm going to start putting a board behind me and putting marks of who's winning, Americans or Europeans.
All right. Well, thank you everybody for coming. It was great seeing everybody and talking to you all. And as always, I learned something from listening to Chris every time I hear him talk. So it was just as much of a pleasure for me. So thank you everyone again, and thank you Jenny for hosting.
Yeah, thank you, Jenny.
Always. And thank you, Chris and Craig.
Good night, everyone.
Good night, everyone. Take care.
Take care. See you soon.